Director General CAPS, AVM Anil Golani, Secretary Department of Defense R&D and Chairman DRDO, Dr. Samir Kamath, Shri Neeraj Gupta, MD MKU, serving and veteran officers, I see many of them, most of them my gurus, from the defense forces and the paramilitary, DRDO scientists, industry leaders, and CAPS members. At the outset, it's indeed an honor and privilege to be invited to be part of this seminar and exhibition, which is focusing on advanced materials and additive manufacturing for defense and aerospace applications. These are contemporary topics of strategic and operational relevance. Without doubt, an important vertical which will go a long way in our quest towards strategic autonomy. Upfront, I must admit, I am humbled by the hundreds of collective years of knowledge which is there in this hall right now, and more so by the presence of Dr. Kamath himself, who made significant contributions to the field of material engineering, high-performance alloys, and indigenous defense technology. I'll be addressing this subject from a perspective of future research as well as the sustenance challenges we face in the Indian Air Force, what we have been doing so far, and what can be or needs to be done in the future. The complexity of operational tempo and environment of military aviation demands high-performance systems having exceptional reliability to be maintained in operational state come what may. Military aerospace manufacturing industry has largely grown around licensed manufacturing of mainly airframe structures built to foreign OEM designs. Engines, aggregates, accessories, avionics are usually supplied as a kit. Whenever these are allowed to be built within India, tight control over the critical parts, technology, processes, and raw material is ensured by the foreign OEM. In essence, we continue depending on the foreign OEMs. Dependency on foreign OEMs, geopolitics, commercial considerations, obsolescence, and OEMs shifting focus to their newer products force countries like us to look at sustenance solutions beyond the OEM. These solutions include developing repair overall technologies, life extensions beyond the OEM specified parameters, indigenization to address supply chain issues, modifications and upgrades, either as a reliability enhancement or a performance enhancement measure. In fact, these activities at the base repair depots of maintenance command have been crucial to the sustenance and enhancing the war waging potential of the Indian Air Force. Typically, a base repair depot addresses the challenges of executing repair overall or the non-availability of an LRU or a subcomponent through indigenous alternatives, either through the industry taking help of DRDO and other organizations like the CSIR, etc. While doing so, we have a plethora of issues to be overcome. The top challenges is the triad of low volume, high variety, and safety criticality. In the context of today's subject, the key challenges, if I may have to take 3 to 4 out of them, material availability to manufacture, to repair, or to overall, developing technology specifications, process parameters and qualification requirements, prototype building and airworthiness certifications, and critically, do it quickly in mission mode. I'm aware that the seminar is discussing advanced materials like nanomaterials, ceramics, and other high-performance materials. I will briefly focus on 3 areas which are of interest to us. Adaptive and smart materials like shape memory alloys enable structures to undergo controlled deformation and recover the original shape in response to thermal or mechanical stimuli. They have got a variety of applications such as morphing wings, adaptive controls surfaces, compacting of the compact actuation systems, and so on. And if we add the capability to embed sensors into these smart materials, this will be very attractive for the next generation structural health monitoring systems. However, the challenges remain in terms of fatigue life, thermal response rates, and integration with composite structures, which are areas for ongoing R&D. Another area I want to focus on is the high entropy alloys, which are emerging metallic materials which exhibit exceptional combination of strength, toughness, thermal stability, and resistance to oxidation and fatigue. Integration of AI and ML with the high entropy alloys is accelerating alloy optimization. AI-driven models enable the rapid screening of vast compositional combinations by learning relationship between composition, processing parameters, microstructure, and resulting properties such as strength, hardness, and thermal stability. This is significantly reducing the time and cost associated with the alloy development. The third area where I want to focus is the thermoplastic composites, which are advanced class of composites materials in which the polymers serve as, the thermoplastic polymers serve as a matrix reinforced with fibers or carbon or aramid. These materials are useful due to their unique combination of mechanical performance, damage tolerance, manufacturing efficiency, recyclability, and more importantly, quick on-site repair to ensure the uptime of the platform. While these are future areas which the seminar will, I'm sure, will deliberate on, I would like to focus on the sustenance challenges what we have. There is a significant amount of R&D work which is going on at the DRDO labs in terms of material development. DMRL, Midani, and so on are at the forefront of it. These materials are crucial for the repair overall and indigenization of airframe structures and engine components. DMRL, Midani, and HAL are jointly working on indigenous equivalents to Russian materials. Russian alloys like Zasha series, AP, EP, and BT series are under various stages of development. A word on the strategic metal bank. Sufficient stock of aircraft and engine materials is crucial for our aspirations to become self-reliant in the aerospace sector. We are aware of how US and China are securing future material requirements. Our efforts to secure strategic materials, including rare earth elements, to establish a strategic metal bank needs a big boost. Retrieval of crucial metals from salvage is equally important in terms of material security. Aerospace materials, particularly for aero engine, is a critical resource. Retrieving materials from salvage engines of phased-out platforms like the MiG-21 and the total technical life expired engines is a feasible option, and efforts are in place to make it a reality. Shifting gears to additive manufacturing, AM is an ideal solution to the sustenance challenges that I had spoken. Low volumes, high variety, and the need to do rapid development. I have embraced additive manufacturing by setting up a facility at the One Central Indigenization Manufacturing Depot, Nasik, in May 22. We have a full-fledged direct metal laser sintering setup to manufacture complex aviation parts. Till date, 400 parts have been 3D printed and are successfully being exploited on the aircraft. Out of these 400 such examples, I will highlight certain key case studies which demonstrate the benefits accrued from additive manufacturing. Acute shortage of electronic warfare pods due to failure of ACS couplings was affecting the op roll of an advanced fighter aircraft. The housing geometry was difficult to manufacture conventionally, and importing the item entailed long lead times. These parts were developed at 11 BRD at a short notice. In another case, the fuel system component failures were occurring in the flight refilling aircraft, which was affecting the op availability of these force multipliers. This was not a high failure rate aggregate, and therefore there was no forecasting or provisioning to get this in our stock. Procurement lead times were at least 24 months. Using in-house additive manufacturing facility, we manufactured this and ensured that these aircraft were available. Similarly, hammer of double-barreled 12-bore gun and the front and rear aperture sub-assemblies of 6-or rifles manufactured using aluminum alloys by rapid design, prototyping, and iteration and production helped ensure that our op capabilities are maintained. It is evident that the adoption of the additive manufacturing technology has revolutionized the maintenance landscape, empowering maintenance teams to rapidly manufacture critical spares. This capability has a direct impact on shortened repair times, increased aircraft availability, and enhanced overall mission readiness. CEMILAC released a guidance document in 2024. This was on airworthiness certification for both critical, non-critical, and low-volume 3D printed components, thus bringing the much-needed clarity on certification and regulatory requirements. There are many challenges in additive manufacturing which we faced over a period of time. Some of them are material quality and consistency, process control and repeatability of achieving specified parameters, non-destructive testing, and understanding the long-term performance with respect to cyclic loadings, which are very crucial for fatigue, and understanding the creep and corrosion phenomena. Equally important is the setting up of a comprehensive qualification system, ecosystem, which includes machine calibration, operator certification, and digital traceability. But the most fundamental problem remains the availability of powders, the material. Since commissioning our additive manufacturing facility in 2022, we operate from 3 feedstock: aluminum alloy ALSI 10 mg, stainless steel 17.4 pH, and titanium alloys Ti6 Al4V. The 400 components what we manufacture are non-critical. Most of them are non-critical. Some of them are critical, airborne components. However, the next frontier lies in manufacturing critical, high-strength components, particularly those subject to cyclic loading and fatigue. Need for specialized materials and feedstock tailored to the unique op requirements, typically characterized by low production volumes, is a fundamental constraint. Addressing this issue needs a structured and collaborative approach involving DRDO, academia, and industry. Such collaboration should focus on the co-development of material systems and establishing valid process parameters. Institutional mechanisms such as the joint research, shared infrastructure, and coordinating funding models can play a pivotal role in mitigating this risk and accelerating the application of AM. More collaborative efforts are underway in this regard. DMRL is working on repair of defective engine components using powder-based laser directed energy deposition, DED technology. DED is a metal 3D technique suitable for complete automation of the repair process and replaces conventional welding, brazing, or coatings. These are standard requirements of a repair overall process. However, the major limitation continues to be the limited availability of powder feedstock materials. DMRL is working on indigenous development of metal powders suitable for additive manufacturing through plasma spheroidization and inert gas atomization process. These techniques lead to improved powder flowability and so on. Midani is in the process of establishing production scale facility for making powders suitable for additive manufacturing. The future of additive manufacturing and its application to on a larger scale critically hinges on our ability to develop critical powders. In conclusion, I would like to extend my compliments to DG CAPS and his team for bringing together all the stakeholders to discuss these critical aspects. I am confident that this forum will serve as a platform for collaboration between industry innovators, research organizations, policymakers, and defense forces. Let's move forward together with purpose and determination. Thank you. Jai Hind.